Hello. Since we didn't have a chance last week to talk about this case study, I wanted to introduce it to you. This video is about a subset of analyses that were done for Beaver Brook Restoration Plan, and that is the activities around assessing non-point source pollution threats to the lower Beaver Brook. And so, this is a team's project. It's basically Jeff Littleton, obviously, many of you know, worked with it. Jennifer Holton was a research assistant who is one of our graduates now. And then Craig and Sean were subcontractors to the overall project. Now, Lower Beaver Brook that we've been visiting, which we've been visiting in this area right here, actually, we demarcated it from the junction of Route 9 and 10 to the north. Beaver Brook, Upper Beaver Brook goes north from that point, but our analysis started at this point, went down through town, this is the square, and it stopped where the Lower Beaver Brook entered the Ashwellet River. And this is it over here. This is a map. It's called parcel map the town has for its tax purposes. And the brook is in blue. The gray areas are the adjacent parcels along the stream, privately owned. And you can see they're numbered, and so we use the numbers as codes as far as the data we were collecting. And if we were doing an analysis like we've done for the stream bank stabilization, we would use the parcel number like 289, and then we break it up into sections. Section 1, 2, 3, and we'd say, right bank, section 1, right bank, section 2, and that means we were always looking upstream. The right bank was always on the right, and looking upstream, left bank on the left. Now, we were looking at some overarching landscape factors that would influence the impact of potential sources of non-point source pollution. You are very familiar with these now. Because of both the TR55 and the universal soil loss equation. But and many of these things we could look at from the desktop before we even got on site. And so slope and impervious surface, soil permeability, all those are desktop. Obviously the buffer issues was done when we had to look at the site. But what's important about these primary site factors is that they would be applied to any potential source of pollutant from any specific lot. And thus, it gave that source a weighting based on these factors that either would exacerbate the pollutant impact or mitigate it. So the non-point source pollutants we're looking at were soils and sediment, primarily because that's how phosphorus gets into a surface water body. And as you know now, phosphorus is a limiting factor for freshwater bodies. Obviously, oil and gas, toxic chemicals, and other sources of nutrients besides soils have detrimental effects within the stream. Biological oxygen demand, BOD, we talked about this. This is any organic material that once it's in the stream and starts to decompose, that decomposition process consumes oxygen and reduces the oxygenation of the water, which could impact very specific species in the stream. Thermal pollution, it's primarily in the warmer months coming off the rooftops and the roads, and most of it gets to the stream through the stormwater system. And similarly, during the colder months, the salts they put down dissolve very quickly and follow the stormwater systems into the stream. We sort of broke our analyses into 4 categories, just sort of the cluster them, which made just sense to us. It could be reorganized in any way, but contamination sources and pathways for those contamination sources towards the stream, BOD factors, that is the oxygenation of the stream water is important. So we looked at things that would reduce it and what was in the stream that possibly could increase its stream aeration. Then we looked at public sector roads. These are things that across the stream or parallel the stream. And so these first two categories, this is what we'd be dealing with as far as landowners and landowner behavior. The potential roads is the Department of Public Works, and so we basically wanted to focus on these separately because these are two different audiences we want to communicate with. And then what was in the stream themselves that actually was a potential threat to the stream just because of built or natural infrastructure. Data sheet, you can see you've seen something very similar to this. Is basically, we had a very simple data sheet, but we had explanations of what people were looking for when they looked at the stream. Okay, and you saw that when we went out to the stream last week, and reading how you would interpret what good, what at risk, and what impacted was. And so the first thing we did was a desktop analysis because that would help us understand each of the lots as we got to them and give us a better idea of potential impact when we were doing site visits. So estimating imperviousness, we did this in class and we did it for this project. And so we would look at each of the adjacent lots and really break down the percentage of imperviousness, semi-imperviousness, and then cover type that could mitigate impacts from runoff. Obviously, the more runoff coming or potential runoff coming, more chance that if there is a source of non-point source pollutants, they have a higher likelihood of coming to the stream. Then we looked at soil permeability, which we talked about when we were talking about septic systems with Pierre. And that is basically how fast does water percolate down through the soils. And that's important, obviously, for this project because if there's water coming off a lot, but it's a high permeable soil, it basically, a lot of that water will go down into the soil. And if it's carrying some non-point source pollutants, maybe those pollutants could be treated by the soil biota just like a leach field. We also looked at soil erosivity. As you know from the universal soil loss equation that this is a factor that one would multiply the other factors by. And so it also gave us a foreknowledge when we went to the sites and we were going to look at stream bank stability and apply the erosion method that you were introduced to, that we'd have an idea of what kind of soils we're actually looking at as far as the potential for erosion. This is basically a map of the stormwater system for the city of Keene. We got this from the town engineer's office. The little squares, the orange or yellow squares, those are actually storm drains, okay, that are in the roads, along the roads that go into pipes. And those pipes connect a number of storm drains, and then they take the water and dump it into the stream through a pipe outfall, and that's what those little dots were. This is an important map to have because as we went up and down the stream, we knew where to expect pipe outfalls, and when we found one we didn't expect, we would mark it for further investigation. We'd go over and see what was coming out of it, if anything, and try to ascertain what kind of material was emptying into the stream at that point. So as I said, you're familiar with a qualitative descriptor such as, with a buffer. And so we came up, and obviously these descriptors were based on research in the literature and based on other similar urban stream analyses around the country. To get this information, as I mentioned, is we had to, go up and down the stream. But the streams themselves were joined by private property, and we made a decision that we weren't going to contact all the property owners, that we were just going to walk the stream since it's waters of the United States. So up where we were at the park and further north, the stream's relatively shallow, and we could get away with either calf boots or knee waders. But when we got down here, this is Roxbury Street that goes into the square, the stream is channelized. It basically, the Army Corps put in and controls a corridor that's a cement corridor. It has cement sides that are higher than the surrounding land, and it has a certain width, continuous. And so what it did is take the waters that were quite wide as far as the width of the stream, and put it into this corridor. It's not a pipe; it's open at the top, and it channelizes the water down through this area, down through places that had been seen to flood quite often, such as Water Street, thus the name. And to go through this, we actually had to use hip waders, and we did this, not during winter. So sometimes the water was quite high, and sometimes it was higher than the hip waders, and so we actually just wore tennis shoes and swimsuits because we had to do some other kinds of monitoring, such as macroinvertebrate monitoring and water quality monitoring at different times of the season. So sometimes the water was high and sometimes it was low. So the modeling of this data, once we collected, is we took the qualitative rankings and we put numeric rankings on them. And then we clustered what we called the primary factors, which I mentioned before, that would exacerbate or mitigate any pollutants that potentially could get into the stream. And those became weighting factors. And then we assessed the scores of each of the assessment categories, such as contaminants, BOD, etc. And then we gave the parcel a threat ranking, which was the average score of all these types of parameters, assessment categories. It's the average score for all of them together for that parcel time the weighting from the primary factors. And so this is just examples. This is just a screenshot of a spreadsheet. These are the parcel numbers, and then we were looking at these are the three primary factors: slope and imperviousness, as you know from the TR55, are related factors that really gives us a runoff impact of the site, and thus it can weight. If we find non-point source pollution, it can definitely weight it one way or the other. Same way for the buffer, with continuity integrity, which you analyzed when you're out on the site. This is a mitigating factor. If you've got a high score here, obviously it's going to reduce the likelihood of non-point source pollution getting into the stream, where this is a exacerbating score. The high rank in this actually will exacerbate the chances of non-point source pollution in the stream. And then there's soil permeability and soil erosivity, which basically is direct impacts right next to the stream as far as stream health. And then we basically had the whole, I couldn't put them all in here, but we had a really long list of secondary factors, or what we call the contaminant factors, and the possible pathways. And so we have pet and animal waste, which was under the BOD, bare soil, etc. We also had stream bank conditions using the erosion method. We had a number of pipe outfalls, and we ranked those. And so what we got is we got a count going across here. You notice that some of these things, there's no numbers in the cells. That's because there was no evidence of these factors for that particular parcel. So we got counts, different types of counts. got total scores, and then we averaged the scores of these type of categories, and then we multiplied it times the weighting, and those we got what we call the weighted score, and it's the weighted scores, which was the parcel threat numbers. So this is just to give you an example of an output, on the Excel spreadsheet for the lot numbers. And we create 4 categories or ranges of numbers so that we could put a color code to them and then translate those color codes to a spatial analysis so that the city could very quickly see, where was those lots that were most impacting the stream. And obviously they're the red ones impact. And so their total weighted score was 0.1 to 30, and that's the range we used, etc. And so you can see, this down here around Roxbury Street, and just north of Roxbury Street, we have some high impacting parcels. Up here, the graveyard, obviously, low impacting because there's not a lot of development there. And then down here at Water Street, there's some areas that are at risk that maybe should be looked at. But it gave the town a very quick prioritization. And we then, we could disaggregate the data in a lot of ways. In this way, we were just showing them the number of parcels that fell under each of the zones for these factors. And so if you look at something like, yard waste, okay, a lot of the lots, there was no problem, but there were, significantly, 6 out of these were impacting the stream. So you actually can come up with a targeted education message and send it specifically to those lots to see if you could solve that problem. And so that, most of a lot of this work would be, educational outreach. On the other hand, we had the road crossings. The roads themselves were controlled by the Department of Public Works, so we had direct access to them. So we could talk to them directly about, their road crossings and the kinds of things we were seeing and how they could change how they might do things. And so, these are some of the things we were looking at, sort of sediment buildup at those road crossings. And the sediment buildup does obviously one thing right away is it reduces the capacity of flow through that box culvert. And so it could create, problems, as we learned from Trout Unlimited, as far as upstream and downstream impacts, not only to the biota, but also possibly increasing erosive forces that would be of concern to the DPW. We found, especially when there were roads right adjacent to the stream, that we were starting to see more excessive stream bank destabilization and erosion. That's because the roads are impervious, and as a result, there's a higher chance of water flowing off those roads and then down these banks. We were finding pipes, and this is, as I said, if the pipes weren't part of the stormwater system, it's sort of like the question is where were these pipes coming from, and what was coming out of those pipes if they weren't stormwater pipes. And then we also found interesting that, any place a road got close to the stream, there seemed to be a lot of times, people wanted to get access down to the stream, maybe for recreation, or maybe it's just a nice place to be in a hot day. But that access point was not official, and you can see that, you have potential contamination of bare soil and erosion that could increase phosphorus loading to the stream at this point. And then we also found that anytime downstream of any place a road across the stream was near stream, we always used to find this kind of situation where people were just throwing things into the water, or the high water during the spring runoff caught things, and then they get trapped in here, from a tennis ball to wood and lumber and that kind of, or basketball. So we highlighted those because those were easy things to solve. And um, doing a stream cleanup day could deal with a lot of those situations. And this is something was very typical. This is Lane's balance. We talked about it. This is rill, R-I-L-L erosion, where basically because of the road, it increases the amount of velocity of water moving down slope because it's impervious, and it will do work. It will cut and move soil. But what's interesting about this is, and you could do this even if you didn't see this erosion, is that where there's armoring or areas in which you have large stones to stabilize the bank, it's probably a good indicator of historic problems. And so it's a little hint that even if you don't see something happening that day, that there probably is something happening over the longer term. So we came up with very specific recommendations as far as non-point source pollution, which is, as I said, this was a bigger project than just looking at non-point source pollution impacts. But for non-point source pollution, it was like targeted outreach and education, changes in operating procedures, especially by the landowners, if we could educate them that way, and definitely by the road crews in relationship to their road restoration or road building and stormwater systems. Outfall tracking, and basically the town needed to follow up on what these pipes were coming into the stream and where they're coming from and what was coming out of them. Stream bank stabilization. The place to start is where the public sector can do it on their own, and so we did point that out, as well as road crossing infrastructure repair and capacity of stormwater through or underneath those roads. If there's an opportunity and they're going to have some kind of major capital project along these roads that we identified, such as repairing the roads or repairing the stormwater systems, possibly looking at green infrastructure, such as permeable asphalt or sidewalks that basically would reduce the potential for runoff towards the stream. Stream revamping is basically, some of these storm drains are well out of current practice, and as a result, it's important that they look at when they have the potential to replace them, so that they actually trap sediment and other materials better, and so that they could be cleaned out and not get into the stream. And then we told them where basically what the next steps could be as far as expanding the analysis and the restoration along mitigating non-point source pollution. Now, just by happenstance, we did expand the analysis because Kevin Chafee, who was in the resource management program, who learned about this project in the watershed course, decided that he was going to do a master's project, and in this regards, he was going to look at the stormwater system that contributed to Beaver Brook, and not just the adjacent landowners. And not only look at the condition of the stormwater system, that is the storm drains, which are supposed to allow materials to settle out and separate the water from the debris, just like a septic system would, so that the water would flow into the stream, and then the debris would be cleaned out. So he was looking at the health of each of the stormwater drains, but he's also using our methodology and applying it to any house that, because of its slope and orientation and the way the driveway drain potentially could have gone into the street and then into the street drains, which meant it was going to get into the lower Beaver Brook. And in his analysis, it really expanded the contribution of the potential of non-point source pollution to the brook itself, and not just looking at the adjacent lands. And so, if just real close up here, here's the brook, and you can see the lots that are in white are on either side of the brook. But if you look at the spatial increase of catchment area or watershed area where non-point source pollutants have come. It's a significant increase in total area of a non-point source pollutant contribution watershed. And so he applied the same rankings that we used in the same way. He did all these himself, where we had a team doing ours, but it was his master's project. And it was an excellent piece of work, and we did share this with the city, and it really opened their eyes to, wow, if we're really going to look at non-point source pollution, it's a much bigger task and dynamic than we initially thought. And so that is pretty much it for the PowerPoint, and I'm hoping that when we get back to class, if you have any questions about that, that you will bring them to class. But I wanted to do this, while we were not in class, so that we could spend more of the time this coming week looking at how to map groundwater and move away from surface water. So